So at second talk, we have Min-Seok Seo from Korea National University of Education, and he will talk about uplift and towers of state in World Road. So please.
Thank you for having me here. So in this talk, I'd like to discuss about the connection between the uplift and distance conjecture in light of my recent work. So to motivate this, let me begin with the well-known fact that whereas lambda CDM model is well consistent with the observational data, so it seems that we are living in the metastable digital vacuum, but realizing this in the string model is not so simple. So models like KKLT or large volume scenario are in fact the result of tuning between the several ingredients of the with the different origins. So we first need a flux compactification and non-perturbative effect in some specific size to stabilize all the moduli, including the Keller ones. But in this case, we will be living in the anti-digital vacuum. So we need to uplift it in addition for realizing the digital space. Such a kind of complexity or tuning gives rise to some question or suspicion that if there is some special region in string theory or even in quantum gravity that makes the digital space unstable or unnatural to realize. So this has been one of the main topics in the swampland program. So another thing I'd like to point out is that many conjectures in the swampland program rely on so-called distance conjecture, which states that the infinite distance limit of the scalar moduli space corresponds to a particular corner of the landscape. So if we go beyond this point a little bit, and then effective theory we have will be no longer valid as the infinite tower of state descends from the UV. So many conjectures like digital swampland conjectures or something like that rely on this distance conjecture. So there have been several attempts to connect this distance conjecture with the very tiny but positive cosmological constant as you observe today. So one of the examples is the ADS distance conjecture, so which suggested the scaling behavior satisfied between the size of the cosmological constant and the tau mass scale. So of course, this is tested just for the ADS string models, but if we can extend this to the digital vacuum, so lambda is given by the size of the cosmological constant as you observed today, and if the tau mass scale is given by KK Kaluza-Klein mass scale, and then it seems that the exponential lambda lies between the 1/4 and 1/2, where the lower bound comes from an observational bound on the large extra dimension, and the upper bound comes from the Higuchi bound. So I'd like to emphasize here that this does not tell us that the Minkowski space is ruled out by this conjecture. So rather, it states the discontinuity between the exactly vanishing cosmological constant and vanishing limit of the cosmological constant, because the latter is very close to swampland due to the infinite tower of state. Another but similar version of conjecture is the gravitational distance conjecture, which comes from the observation that the size of a cosmological constant in ADS vacuum is smaller than the 3 times Planck scale squared times the gravitational mass squared. So the equality is of course saturated for the supersymmetric case. Then it may be the gravitational mass rather than the size of a cosmological constant that satisfies the scaling behavior with respect to the tau mass scale. But these are in any case the generic story. So let me just focus on in this talk in a model building point of view, which of ingredients, namely the flux effect or the non-perturbative effect or the uplift, so which satisfy the scaling behavior with respect to the tau mass scale. So in other words, which can be directly connected to the distance conjecture. This is the question I'd like to ask through this talk. So for this purpose, I focused on the specific but well-motivated model. So I mean that the KKLT or large volume scenario is based on. So Type IIB plus compactification, which contains the warped deformed conifold, and uplift potential is produced by anti-D3 brane at the tip of the throat. So the conclusion of this talk is that, in fact, when the uplift potential is produced by anti-D3 brane, it reflects the geometry of internal manifold through the, for example, warping factor and volume of internal volume. And this is, in fact, very closely relevant to the tau mass scale. In particular, we can consider the Kaluza-Klein modes. So anti-D3 brane, uplift potential is very naturally connected to the distance conjecture. Okay. So to see this, let me just focus on the legend near the Klebanov-Strasser throat. So where the 10-dimensional metric is written in the factorized form. So here sigma is the scalar part of the volume modulus, and A provides the warp factor. And this exponential omega is in fact the Y factor. So if we match the 4-dimensional Planck scale after compactification, we can fix this to be inversely proportional to sigma to 3/2, and also vacuum expectation value can be taken to be 1. So typically the warp factor is parameterized by exponential minus 4a. So when it deviates from 1 significantly, we can say that the magnitude of the fluxes on the geometry is very large. So storage is strongly warped. But storage is not so simple as expected because. So, for example, if you consider the some stabilization of the conifold modulus Z, which is stabilized at the exponentially very small value, so where the exponent is given by the ratio of the fluxes, and then it consists of two terms. And the second term is nothing more than what appears in the warp factor, so which I call the warping term. So it should be compared to some logarithm, which is interpreted as a Thorne length. So when this warping term is much larger than the Thorne length, and then in almost every case, the warping term is dominant in almost every case. So we can confidently say that the storage is strongly warped. But there is some cases due to, for example, the very large volume, the warping term is rather suppressed compared to the Thorne length. So in some literatures, this case is called the weakly warped storage. But we also know that the throat can be even more weakly warped. So for example, if the warping term is much smaller than 1, so warp factor is approximately 1, and then the throat is more weakly warped. So I call this the extremely weakly warped case. But even in this case, the warping term may be larger than the throat length. This is because whereas when the conifold modulus is stabilized at the value very close to order 1, and then Thorne length will be very close to 0. Okay, but I think this is not so sensible, in some sense, some physically. So the reason of which will be discussed later. Okay, and let me also point out the well-known fact that the warping term is inversely proportional to Z2 third and inversely proportional to the square root of sigma. And there is a cancellation. So I mean that the 6-dimensional manifold is overly proportional to inverse the square root of the sigma, so we can expect the cancellation of the sigma terms. And also internal manifold described by the Klebanov-Strasser throat is overly proportional to Z to thirds, so we also expect the cancellation of Z. So the only dependence on volume appears through this string length scale. So in this case, this is actually cancellation that well known for the when the warping term is much larger than 1. Okay. Then which kinds of Taurov states we can consider? So first of all, we can consider the string excitations. The characteristic mass scale is given by string mass scale, which is suppressed by compared to the Planck scale by the square root volume, where the volume is given by vacuum excitation value of the sigma to 3/2. And since we are considering the compactification, so we cannot omit the Kaluza-Klein modes, but its mass scale depends on where the KK modes are localized. So for example, if we consider the KK mode living in the Thorne region, and then its KK mass scale is given by exponential A, originate from the warp factor, and also gives a Redshift effect, and also inversely proportional to the typical length scale of the 6-dimensional manifold. So as I just mentioned before, so when the warping term is it's much larger than 1, and then actually we expect the cancellation of the Z and sigma. So this is actually roughly given by exponential A, Redshift factor times string mass scale. So as a result, actually KK mass scale is proportional to Z2 to 1/3 and inversely proportional to volume to 1/3. So, and moreover, when this KK mode is localized along the B cycle, and then this is inversely proportional to Thorne length. So when Z is much smaller than 1 and volume is very larger than 1, and then Thorne length is much larger than 1. So in this case, the KK mass scale is the lowest tau mass scale. But when the warping term is much smaller than 1, I mean the extreme weakly warped case, and then we cannot expect the cancellation of Z and sigma. In this case, actually, the KK mass scale is not so light as before. So it is actually larger than, heavier than, or very similar to the bulk KK mass scale, which is just inversely proportional to the volume 2/3, which does not depend on the size of jet. Okay, so whereas typically the KK mass scale is the lowest tau mass scale, so when the warping term is much larger than 1, the through KK most corresponds to the lowest tau mass scale, and in the extreme weakly warped case, bulk KK mass scale is the lowest tau mass scale. Okay, then let me move on to the uplift potential produced by anti-D3 brane, which are extended over the non-compact 4-dimensional space-time. In this case, the induced metric is given by this form, the 4-dimensional part of the 10-dimensional metric I just showed before. And its uplift potential is actually given by the sum of dBi and Chern-Simons action, so which are the same in size. So this is the origin of this factor 2, and also proportional to the brane tensions, which is proportional to string force power of the string mass scale. So since you see that the vacuum expectation value of this Y factor is taken to be 1. So its size of the uplift potential is in fact force power of the string mass scale times exponential A. And this is so this is nothing more than what appears in the KK mass scale in the case where the warping term is much larger than 1. So we can immediately find out the scaling behavior satisfied between the uplift potential and the through KK mode, so where the exponent is given by 1/4. So this was already pointed out by the work of Blumenhagen, Brinkman, and Macri-Dot paper, and this impact is that motivated my work. So I wonders, is there a special reason for this scaling behavior, and also what happens if the warping is not so large. But I'd like to comment on one thing. So originally you see that the uplift potential is given by this, where this comes from the exponential A, so inverse of the warp factor. So here the eta is interpreted as a portion of anti-D3 brane in the third region. So originally we have to see where these anti-D3 branes are stabilized by looking up the behavior of uplift potential with respect to eta. Of course, typically you see that this is a monotonically increasing function of eta. So the potential is minimized at eta equals 0. So I mean that typically the branes are stabilized at the tip of the throat. But when you see that this warping term is very small, so there is some subtlety. It is quite suspicious if the anti-D3 branes are well stabilized at the tip of the throat. So of course, you see that if warping term is very small, actually the potential increases very slowly. But in any case, the potential is in any case minimized at the tip of the throat. So if we consider the basic quantum mechanics example that the very shallow potential well, and then in any case we can always find, even if the potential is very shallow, extremely shallow, the bound state exists. And since you see that the potential is in any case the minimized at the tip of the throat, we can say it is most probable that the anti-D3 branes are localized at the tip of the throat, even if we can find some sufficient probability to find out the anti-D3 brane at other place of the throat and even outside the throat. But the problem maybe becomes very severe when the throat length is extremely small. So I mean that even in the extremely weakly warped case, the throat length may be even suppressed compared to the warping term. So in this case, actually, this potential, I mean that the throat region itself ends even before this uplift potential increase sufficiently. So in this case, actually, the probability to find out the branes even outside the throat is not negligible. So I think it's suspicious that the uplift potential is well defined in this case. But in any case, it is also actually the behavior of potential inversely proportional to the sigma to third is maintained. So you may consider this if you want. Okay. So in any case, in this case, in the extremely weakly warped case, actually, since the warping factor itself is very close to 1, and this the phi factor has a vacuum excitation value very close to 1, so we just find out that the size of omnipotent potential is proportional to force power of the string mass scale. So we can immediately find out the scaling behavior satisfied between the omnipotent potential and string mass scale, where the exponent is given by 1/4. So in any case, we can find out the scaling behavior where the exponent is given by 1/4. And this the origin of this factor 4 comes from actually the dimension of the non-compact dimension over which the anti-discrete branes are extended. But in the extremely weakly warped case, the string mass scale is not the lowest tau mass scale. Then what? So we can see if you can find the scaling behavior for the lowest tau mass scale, so namely the Burke K mass scale. And of course, we can find this is because so when the warp factor is very close to 1, actually, the omnipotent potential just scales like a volume. And so this can be directly connected to the tau mass scale living in the bulk, so not in the third region. So we can find out the scaling behavior satisfied for the Burke K mass scale as well. Okay, so discussion so far shows that the omnipotent potential produced by anti-discrete brane satisfies the scaling behavior with respect to lowest tau mass scale, so KK mass scale itself. And away from this, there already exists the tau mass scale with the exponent is given by 1/4. Okay, so I think most of you are very well aware of what I have been talking. And I think some of the results are very well known facts. So, but let me just advocate the result I just show you and what is special in that. So, in many cases, in many literatures, actually, the size of the omnipotent potential is typically identified with the size of a cosmological constant of the ADS vacuum before Uplift. But this is in any case because we want to realize the very tiny cosmological constant is observed today. And there is a priori no reason that the omnipotent potential and ADS vacuum size are the same because their origins are completely different. So I'd like to point out that we need to distinguish the origin of these mass scales, and actually the connection to the tau mass scale is one of such kinds of example. Okay, and for example, if you try to realize the inflationary scenario, and then actually the omnipotent potential may be much larger than the ADS vacuum size, for example. Well, of course, it depends on the model. And another thing I'd like to point out is the discontinuity. So this is because you see that the scaling behavior is satisfied only if the number of anti-discrete brane is non-zero. But in any case, away from the existence of the anti-discrete brane, actually the tau of states exist and tau mass scale exist. So if we try to realize that, for example, ADS vacuum without the omnipotent potential, we just be careful that the effective theory we have is decoupled from the tau mass scale. But once we introduce the omnipotent potential produced by omnipotent anti-discrete brane, we must be careful, because even if we try to realize the same ADS vacuum with the very tiny omnipotent potential, and then this will not be allowed as the tiny omnipotent potential accompanies the descent of tau of states, so effective theory will no longer valid. Okay, so such kind of discontinuity actually reminded me of the some discontinuity emphasized in the ADS distance conjecture or the gravitational distance conjecture. Okay. Actually, in many cases, there are some regions that omnipotent potential is quite sizable. So, for example, so for the effective theory we have will be valid. Actually, we have to see if some typical mass scale of the effective theory can be much smaller than the tau mass scale. So, for example, if you try to consider the four-dimensional effective supergravity, and then gravitational mass scale should be much smaller than KK mass scale. So in this case, actually, this is another way to impose the upper bound on the lower bound on the omnipotent potential. And moreover, since this actually the gravitational mass scale is directly connected to the size of the some superpotential. So this is one way to see that how much tuning we need to realize that, for example, tiny but positive cosmological constant. But there is a very well-known some subtlety that when the warping term is much warping term is much larger than 1, actually the through KK mass scale is rather smaller than the conifold modulus mass scale. So in this case, we have to see if the theory is very well controlled, and this has been already studied in this literature. And also, but whereas you see that so I have been talking about the size of omnipotent potential, but there is also there is some counter the reasoning that omnipotent potential is not should not be too large. So, for example, if we consider the simplest model, by simplest I mean that for example, non-perturbative effects consist of a single some dominant terms. I mean that I don't if we do not consider the compete between the two different kinds of non-perturbative terms, and then in this case, actually, the potential before omnipotent is has a very simple form. So in this case, when omnipotent potential is very large and the potential will be omnipotent too large, so the total potential will show the runaway behavior. So in this case, modular stabilization will fail. So this is another some constraint on the omnipotent potential which imposes the upper bound. So for details, I actually some you can refer to by recent paper because the details are not so simple. Okay. Okay, so this is all right prepared. So thanks for attention. Okay.
Okay, thank you. Thanks a lot. So now we have time for question. Okay. Meanwhile, maybe some other question come. So I have one question. So if I understand well, your result concern. So you're saying that basically, when the uplifting potential in the limit of the uplifting potential going to zero, you see that the effective field theory breaks down, right? But see that which kind of tower of states. I mean, what happens in this limit? So you say that you put like a lower bound, an upper bound. Okay, the upper bound, I think it was known already because like you have the destabilization of the volume modulus. But when you go like to the limit of B up going to zero, what happens in this limit?
So you mean that the vanishing limit of the omnipotent potential?
If you understand well your talk and your paper is, you say that when V up goes to zero, you get like I mean, you get a lower bound on V up, right? On the uplift term.
All right, right. So yeah, you see, so yeah, this is a FCM passage. So I mean that when the omnipotent potential is very small, and then this accompanies very tiny mass of the tower of states, so effective theory will break down. So this is one thing.
I see. So, but in principle, like if you start like with the sitter, I mean, if you start like with anti-de Sitter, then you add like your uplifting term and you go like to the sitter, right? So you're saying that going from the sitter to anti-de Sitter to the original anti-de Sitter, like you break. I mean, you find like a breakdown of the effective field theory.
Yeah, so if the ADS before omnipotent has a very tiny cosmological constant, I think the theory will be very dangerous. Because the omnipotent potential should be very small, so it accompanies the some descent of the tower of stage.
But somehow it seems to me that this process is still like not compatible with the ADC with the anti-de Sitter conjecture, right? That's because like through this process you are you're able to pass from like a DS effective description to a Minkowski and to DS, but you don't see any, right?
I think it is rather close to the gravitational distance conjecture rather than the ADS distance conjecture, because the ADS distance conjecture is concerning the size of cosmological constant itself. I mean that the result of the Uplift or something like that. But the Uplift potential has to do with some kinds of I think it's close to the ADS distance conjecture if we focus on the tiny cosmological constant to realize the current universe. But we can consider for example, considering the realizing the ADS vacuum or some inflationary scenario with a much larger omnipotent potential, and the situation may be some generalized by some considering some connection between the omnipotent potential and Taurov stage.
Okay, thank you. So, other question? Seem there are no other questions. So in this case, I would like to thank both speakers of today.